is being recorded.
All right, welcome everyone to the January 16th Eclipse OMR Architecture Meeting. I'm Mark, sitting in for Daryl, who's, I believe, sitting on a plane right now. Today we're going to be hearing from Mark Palm about his work to port the OpenJ9 shared class cache technology into Eclipse OMR. And so I will pass over the reins to Mark. Take it away, Mark.
Thank you. Can you hear me?
Yes, we can hear you.
Oh, okay, great. Okay, so this is a high-level overview of the work I've been doing in the past 8 or 9 months or so to port the OpenJ9 shared class cache over to Eclipse OMR. And primarily, this was done with an eye towards achieving backward compatibility with the OpenJ9 shared classes cache. But also done in such a way that would enable people to both understand the cache at a high level and to be able to adapt it to their own runtimes. So let me just try and see if I can figure out how to go forward in this. This is kind of, I'm on Georgi's setup actually, so this is a bit new to me. So let's see. Yeah, there we go. Okay. So just to give you an overview of what I'll be presenting when I talk about the general goals of the shared class cache as realized in OpenJ9. I'll give you an idea of what the architecture of the OpenJ9 shared class cache looks like for those of you who aren't familiar. And then we'll take a look at the refactored shared cache. And the entire purpose of explaining the architecture of the OpenJ9 shared class is just to motivate the concepts that we find in the refactored shared cache. And I should also say that all of this material has been culled from the paper that I submitted to CastCon 2019, which was rejected incidentally. That's a much deeper dive into the material that I'm going to be covering here. This is going to be a very high-level overview, so I imagine that you'll have questions from like all sorts of potentially different angles, so that should leave us some time for discussion. Okay, so just to remind you, or if you're not aware, the goals of the shared class cache in OpenJ9 is, of course, to share various kinds of data between multiple running OpenJ9 virtual machines that are either running within the same process space or across a network or what have you. And examples of these metadata include both JIT and AOT compiled code, the read-only portions of Java classes, strings that have been persisted to the cache, JIT profiling data, and quite a few others. I'm not going to bore you with the details, but suffice it to say, it's quite a versatile collection of data that a cache can store. So if we start at the lowest layer of the cache, that would be the OS cache. And I'll show you a truncated version of the OS cache class hierarchy in C++ in a minute. But generally what the OS cache classes determine is the manner and the location of where the cache is located in memory. And it determines how that memory is accessed and provides primitives to the caller to allow that memory to be accessed, to be synchronized, to enact different levels of page protection. There's quite a few different things that you can do, of course. I'm not going to name all of them. If you want sort of a compacted example of how the OS cache decides which version of the OS cache to implement, when a shared cache is instantiated from within OpenJ9, there's this function, which is sh_os cache : new instance. If you do a GitHub search for the file oscache.hpp in the OpenJ9 repository on GitHub, you'll find it. And that's kind of a nice representation of how the cache is instantiated according to, I believe it's command line options. It's been a while since I reviewed that section of code, but I believe that's where it happens. So here's the promised OS cache class hierarchy. So you start at the top from the most abstract level, and then you just sort of drill down according to whether the cache is either persistent or non-persistent. So persistency means that the cache survives between separate invocations of OpenJ9 instances. Just to say that if a persistent cache is first created, then after the last connecting VM disconnects from it, it continues on disk as a file. And subsequently, future instances of that application running through OpenJ9 and map that cache into memory using the mmap primitives that we find in the OMR port library. Within the OpenJ9 design of the class, there's this intermediary class called OS Cache File, which, as you might expect, contains a bunch of intermediary routines for treating the cache as a file. And then lastly, we have OS Cache sysv, which is the non-persistent version of the cache, which just exists in shared memories managed by semaphores. So sysv, I think it comes from the system V architecture, which is where that whole set of inter-process communication primitives comes from. But of course, it's using the OMR port library, which is to say that obviously its reach is much broader than simply systems that incorporate or are descended from system V. Okay, so that's the class hierarchy. If we move up one layer of abstraction above the OS cache, we find the Composite Cache, which actually implements the various techniques for synchronizing primarily, synchronizing and allocating memory to different parts of the cache. Those parts of which I'm going to refer from now on as regions. Another task that it incorporates is to enforce certain options selected by the user from the command line in a way that the OS cache really does not. The settings are kind of handed down to it from the Composite Cache. And it's at this layer that we find this visual representation of what a cache block looks like in memory. So in the past, it was actually possible for people to chain multiple instances of cache blocks together. I think that functionality has been removed, but it used to be, for some reason they used the terminology nested cache. I wasn't really certain of the reasoning for that choice of name. But in general, if we suppose that the cache just exists on a single contiguous block, this is the layout. So if we progress from left to right, the cache header contains all of the common configuration data that's used to identify the location of either byte locks or semaphore sets, depending on the semantics of the OS cache. Contains various runtime configuration flags. It can be used to identify distinct OpenJ9 VMs from those configuration flags. Is just one example application of what I might mean by those. It indicates when the cache was last connected to or modified. General information like that. So diagnostic and configuration data. Did I lose connection? I just heard a beep.
No, we can still hear you.
Okay, I'll continue then. So just working our way from left to right, we find that the ROM class segment list, true to the name, contains ROM classes. And when I say that it grows forward, I really mean that it just grows to the right, so starting at the left, at least in memory. If you imagine this segment is going from the top down, we're actually marching downward in memory to the lower addresses. The ROM class segment list just contains ROM class representations. Well, on the opposite end, metadata entries contain various stubs that point to the location of various bits of data within the cache, and that grows in the opposite direction. And between the two, there's this region of empty free space. And I believe the default policy in the OpenJ9 cache is to maintain a buffer of 1 kilobyte, separating these regions from one another. If you attempt to violate that, then I think the cache simply refuses to allocate any more data. So that's an example of an allocation policy between separate regions of memory, which is going to figure kind of prominently in the redesign later on. And lastly, at the top of the class hierarchy, we have the cache map, which talks to the composite cache object. And the cache map is largely a runtime layer. And I believe its responsibility at startup is to actually iterate over the entries within the metadata layer and to fill various hash tables and other lookup structures that the runtime will use to actually retrieve data from the cache. And just to see some examples of these hash tables, they're organized into this manager family of subclasses, which are usually specialized around the type of data that they manage. So it's pretty immediately evident from the examples that I give here. You have ROM classes, like compiled methods, classes, class paths, different timestamps, among many others, of course. Okay. So with that out of the way, we're about prepared to talk about the refactored OS cache, which largely tries to divvy up the function of the OpenJ9 classes into a set of smaller and one might say more intelligible, more specialized classes. With most of this is done with a view to just making the design of the cache a bit more intelligible to an outsider, someone who's perhaps using OMR but isn't really familiar with the intricacies of how inter-process communication works or exactly how the OpenJ9 shared cache does things. And while we want to achieve that aim of basic just intelligibility, we also want to ensure that there's an amount of precision and customizability allowed by this approach. So with that end in mind, there are three main topics that we could discuss. That's just listed here in this list: cache structure and layout, extensible configuration, and I call them additional features because they're kind of ancillary, like they're not really essential to the core operation of the cache, but they can be used to enhance functionality in various ways, which we'll talk about when we get to that section. So as I told you before, we start with this initial idea of dividing the cache into regions whose purpose is specialized towards whatever data is being held within that region. Okay, so all that we assume within the refactor shared cache, intrinsically speaking, is that every region has a unique identifier and belongs to a single cache layout. So the cache layout is a manager object that effectively owns all of the runtime objects that represent each of the cache regions. And it's meant to allow a means to mediate disputes between regions. So when we covered the composite cache layer a moment ago, I mentioned to you that the ROM class segment list and the metadata area allocate toward one another, and that it's possible to have a quote-unquote dispute between the two if they try to allocate too close to one another. So that's an instance of what I mean by the word dispute in this case. So just to give you a really brief idea of what this interface looks like, we have these three pure virtual functions in C++. I just identify the start of the region, the size of the region. And the predicate function is address in region, which indicates whether an item at an address of a certain size is contained within that region. And the only data members that it contains are, as I told you, the ID and a pointer to its own layout. So diagrammatically speaking, that just means that OS cache layout owns a vector of pointers to region values, which then point back up to the layout. So this way, if a region has a dispute with its neighbor, it can submit its ID to its own layout object, excuse me, and then the layout object can retrieve both of those region objects from its vector, and that's rather straightforward and simple. That's just the general idea. As I said, because it contains pure virtual functions, it's in effect an abstract class, as you'd call it in Java. So what that means is that we expect it to be subclass, and for the subclasses to provide those methods. So the only subclass of the region class that I provide within the refactored version of the shared cache is OS Cache contiguous region, and I'll probably contract that name eventually. But contiguous region just is what it says in the tin. It's just a contiguously allocated region. The OS Cache region base class tries not to make the assumption that a region is allocated either contiguously or in any other way. It's just a general interface, just that we have this thing and it lies somewhere in memory, and where it's stored and how its contents are distributed throughout memory, we don't really know anything about. So the member functions of OS Cache contiguous region are pretty straightforward, probably exactly what you got in mind. I don't really think I need to talk about those. With regions comes the idea of a focus. And the notion of a focus is developed to apply in two specific contexts. So if you recall before, I told you that the cache header in the OpenJ9 shared cache stores configuration data that's common to all client VMs. Very often that involves dealing with one or a handful of words within the header. So an OS Cache region focus is essentially just a pointer around an object of type T because it's a template, template class, which by default cannot be reseated. As well, it contains a pointer to the object's region of residence. Perhaps I should say field. I don't think object is really totally appropriate there. And then when you set the region at construction time, there's some bounds checking just to ensure that the location you provided actually points somewhere within that region. So this would probably be a good time to point out that I don't use anything like RTTI or exceptions. The refactoring that I do apply mostly just consists of C++ templates combined with just old-fashioned polymorphism, just virtual functions mostly in templates. So I'm not throwing an exception in the case that the bounds check fails. I'm really just like making a TRC assert within the body of that constructor, just to clarify how that's done. I should also specify that it's the owning region that's deferred to confirm that the focus is contained within that region. OS Cache region bump focus is kind of similar, except that it actually allows the focus to be changed. And that's mostly to accommodate the use of bump allocation in various regions, like we saw in the OpenJ9 shared cache. So in this case, you can select a direction and you can either bump down or up. In this case, the plus and plus equals operators are the only modifying operators defined, but beyond that, there are comparison operators just defined using operator overloading, so that's no big deal, really. After each bump, there's again a bounds check using exactly the same means that I described on the previous slide, except this time, rather than failing with a failed assert, it just returns a null pointer. The reason for doing a assert at instruction time in this case is likely because this is something that you would expect to fail at cache initialization. I think that's just sort of an assumption I made that's maybe not too well-founded, but from what I know of the OpenJ9 cache, that type of thing usually causes the entire thing to fail. And by thing in the last instance, I just mean like cache initialization. Okay, so that's regions and layout. Now the next topic of 3 is, second of 3, I should say, just refers to configuring the cache. which I assume to occur primarily in the header. I do have a separate structure that's dedicated to runtime configuration data, which we'll discuss shortly, but just focusing on the header for now. We should note that the OS cache mmap and sysv, the previous persistent and non-persistent versions of the OS cache in OpenJ9, also, they both define their own fields inside of the cache header that they kind of append onto the core fields that the OS cache subclass supposes. Yeah, so the exact configuration and contents of the header actually varies quite widely in terms of which fields are included, what order they appear, based upon the Java version that OpenJ9 is running and the quote-unquote generation of the cache, as the design has termed it, that's being used. So as the cache changed and evolved over time, so too did the header. And the way that was handled in OpenJ9 was through the use of preprocessor constants, I suppose, like just C preprocessor flags. That can be toggled on or off to just enable or disable certain parts of the setup. I tried to get away from that in this case and just do something that was, I guess, more idiomatic by standards of modern C++. The techniques used in the design of the OpenJ9 cache kind of go back to more C and aren't really so C++ oriented. But yeah, if you want to have some idea of what's typically contained in the cache header, I think I kind of alluded to this before actually. But in this case, we have the eye catcher for various logs, the creation time, last time the cache was attached, last time it was detached. Again, you'll probably also find like the VM ID or byte locks in there. Various things. But the point is that depending on the version of the cache and the cache semantics, the contents of the header might change. So one of the nice things about C, of course, and just being able to manipulate pointers is that once we've instantiated a struct representing the contents of a cache header on the stack, we can just align the address of that struct to point to the head of the cache. And just immediately all the fields of that struct will be populated. That's quite nice to do. That's obviously much less error prone than just filling that all up by hand. Not to mention less verbose, so I'd really like to preserve that. And naturally, the first thing that I reached for to try and accomplish that was class inheritance in C++. I found that to be a bit too inflexible even for OpenJ9, which is takes a fairly conservative approach to its use of C++ over C. Even OpenJ9 avoids that because class inheritance just doesn't afford the flexibility that they need. So I took this alternative approach of, I suppose it's a curiously recurring template pattern, excuse me. Not entirely sure about that. But in general, I have this undefined template class whose specializations in either the memory mapped or shared memory revisions of the caches basically just define associated types called mapping type down here. I don't know if you can see my cursor or not. You also notice that I changed the name OS cache mmap to OS memory mapped cache. It's a longer but much more readable name, but it's essentially the same thing. So along with renaming the OS cache mmap and OS cache sysv to these, I also introduced these header classes from within C++ just to encapsulate all the header logic, and they in turn own these cache header mapping impl t objects, which in turn own these cache header mapping t pointers, which actually are the pointers that point to the heads of the cache. So this is just to have like a consistent layout, because often in most C++ implementations, when you define classes that contain virtual pointers as cache header mapping impl does, and you end up with a hidden pointer to a vtable somewhere, and that can really mess up certain expectations of how that class is going to be laid out in memory. So the purpose of these impl classes is to subsume casting functions as virtual functions, meaning that they're dynamically overloadable and dispatched to, while also retaining information about these cache header mapping pointers, the contents of which actually define the structs, or excuse me, the fields of the cache header and their layout. And often it's much more flexible to just take the cache header mappings that I have defined for the OS memory mapped cache and OS shared memory cache, and to just compose them with any subclasses of these mappings. So that, like, if I introduce a new cache, which inherits from OS memory mapped cache, for instance, and I introduce my own custom header fields, I can just include the mappings that are catered toward the core OS memory mapped cache as a field within that header mapping. And then combined with the visitor pattern, which is kind of glorified / poor man's version of pattern matching for C++, you can reuse a lot of the previous logic that we used to initialize and serialize cache headers. So I'm just kind of introducing this sort of goofy terminology here. So serialize just means that when the cache is first created, the header has to be set up. And when the cache is connected to or attached from on disk, or say a shared memory snapshot, certain fields may need to be updated again, but others are going to be left exactly as they were. So it's a different process, depending on whether you're creating a new cache or just initializing an existing one. The visitor pattern in this case allows you to pattern match over different object types. And it's particularly nice for reusing code that we previously used to visit objects belonging to superclasses, because then we can just rerun the visitor on the superclass object and then sort of append our own logic onto that just as sort of an addendum. So that's kind of convenient. Yeah, okay, so this is some of what I just told you. Yeah. So regions are serialized at creation time, initialized at connection time, you might call it, or maybe reattachment would be a better word. Yeah, this is everything that I just told you. Okay. So that's all I'm going to say about header mappings for today. I mentioned that I would say something about the OS cache config class, which subsumes all of the runtime configuration data. That's quite straightforward. Once again, there's specializations of this core abstract base class, according to whether you've got the shared memory or memory map semantics, which can again be derived by custom created caches. OS cache config options is a builder class that we use to specify configuration options to the cache. Because the OS cache operates entirely on top of the OMR port library, it, at least in OpenJ9, contains like a lot of specialized knowledge of how the OMR port library works. So part of the idea of the config options class is that it knows how to talk to the OMR port library, but it represents the configuration of those options at a much higher level to the user. They don't necessarily need to be that familiar with the OMR port library in order to configure the cache. So you can use a builder pattern. This is all in my builder class in this concept to specify what the options are, and from there on, internally, the config options class can render those options to a bit vector that's understood by the OMR port. That's all that's really happening there. Lastly, as far as the refactored cache goes, I mentioned additional features. So in my view, the cache is primarily about storing, finding data, and coordinating access to data through different means of synchronization. That's its core functionality, and everything on top of that is essentially just sort of gravy, depending on what you view as being essential. So the OpenJ9 shared class subsumes all of these additional features among many others, but most of these that we would consider important, of course, are just page level protection of different regions of the cache, detecting corruption by performing cyclic redundancy checks, gathering statistics from the cache header and reporting them on the console. There's a command line option for that in OpenJ9. And there are additional primitives to support more sophisticated types of locking. In the OpenJ9, there are a few, in the OpenJ9 shared cache, there are several instances where you might want to lock the cache entirely, which is to say that you want to forbid all writes to the cache until we say so. Well, forbid is the wrong word. Really, the word that I want to use there is block. Yeah, you want to block writes to the cache until some read is finished. So these additional features are just provided as additional classes. And in the pull request that I made of this, these are generally marked by like anything not beginning with OS cache, I consider an additional feature. And generally they build upon some of the previous primitive instruments, classes rather, that I introduced previously. So synchronized cache counter just wraps an atomically guarded counter somewhere in the cache. It does that by wrapping the counter up in a focus object. And then it either increments or decrements the count atomically using the OMR port library. But generally, like how it does that, like for instance, the atomic synchronization, like the exact means of that is just hidden away within the cache. It's not exposed directly at the caller level. So it's really just more about convenience than anything. Memory protection is another instance where the virtual visitor pattern could be beneficial, say if memory protection policies differ over different regions. Likewise for producing CRCs. Yeah, so once you've like grappled with the core concepts that I explained in the previous two sections of the refactored cache, you'll see that the additional features just add their own functionality based upon what we saw earlier. So there's really not much more to elaborate about it beyond that. If you want to see a demo version that consumes the refactored cache, over the summer, Peter Yankovic and Georgi Krylov and I did some work on extending Charlie Gracie's previous extensions to the SOM++ Smalltalk interpreter, where he added a compilation component in JIT Builder. Prior to that, it was just purely a Smalltalk interpreter. We adapted that to use the revised cache to store its own internal representations of Smalltalk classes, compiled code, relocations of various types. Before that, we adopted the shared class similar manner for use with WASMJIT, which was a product of Leonardo Bandarelli and Benjamin. His last name is Thomas. I don't know, I might have mangled that, but yeah, they did some work taking the WASM. What was it called again, Peter? Yeah. Prior to WASMJIT, though, there was some project that was intended to be a reference implementation of WASM. Right, WebAssembly binary toolkit. Yes, that's right, WABIT. Okay. Yeah, they added a JIT to WABIT in a similar manner that Charlie added a JIT to SOM++ using JIT Builder. So we did some work with that as well, just storing code in that case. WASM is a much simpler and less dynamic language than Smalltalk, so in many ways it doesn't pose the same technical challenges that designing a good cache for Smalltalk would. yeah, that's basically what motivated the design of the Smalltalk cache. If WASM had been a bit more dynamic or difficult, depending on your point of view, we'd have likely stuck with WASM. But yeah, I have a talk that I dedicated to that I gave at CASCON 2019. If anyone is interested in those slides, I can just send me an email, I suppose. I told you all about the first item already. The second contains some example uses of additional features that I've been telling you about, all of which are also found in the OpenJ9 shared cache. Okay, so that's all that I have today. Thank you.
Thanks, Mark. I had a question. You used the word refactored a few times to describe this work, but you didn't talk about how what you've created fits back into OpenJ9. Does it fit back into OpenJ9, or would it require additional rework?
It would require additional rework.
Yeah.
Definitely, yeah.
Okay, but you're confident that rework would be practical?
Yeah, I think it would be practical, yeah. I'm not sure that it would like necessarily boost performance or anything, which I know is a very key importance to the OpenJ9 people. But...
Right. Okay, so performance would be one concern. Are there any other concerns that you can forecast for that?
For the OpenJ9 shared cache?
Yeah. Shared cache.
I'm not really sure what the priorities of the designers and maintainers are currently. I guess one thing that this could offer, like as I said before, is just better compartmentalization of various features. It gives a person a better idea of how the cache is organized, or how it operates or can be thought to operate, I suppose, just as a conceptual model.
Okay. Can you talk a little bit about what data was being stored into the shared class cache when you were running it as part of Smalltalk?
Yeah.
So I know in OpenJ9 it's ROM classes and JIT code and profile data and et cetera, et cetera. I'm just curious if you could talk a little bit about what you stored in there for Smalltalk.
Okay, yeah. So there's representations of all kinds of different Smalltalk classes, which doesn't sound like too much, but it's actually a fairly wide range of stuff, considering that in Smalltalk, literally everything is a class. Classes themselves.
Is a class in Smalltalk like a ROM class in Java, or does it have portions that are constructed at runtime as well, or? Did you have to break a Smalltalk class into pieces the way J9 breaks classes into pieces?
Nope, no, we didn't. No, we just serialized them and deserialized them. So.
Okay. Interesting.
But yeah, that part is fairly straightforward, actually. That's kind of its own little branch of logic there. In terms of how you can like represent them in binary and then get them back out again.
And is the representation, sorry, you talked about how the different regions are built in the OpenJ9 shared cache. Is that similar in terms of the OMR shared cache that you've built? So its compiled code fits into the metadata type section, or does it have its own kind of section, or?
It's entirely up to the user. So when I refer to the OMR shared cache, what I'm really referring to is like a type of a builder in the sense of JIT builder for shared caches. So it makes no presumptions about how many regions there are, how they're laid out, or what their types are. And it's all up to the end user to decide.
Okay, so how things get added to the cache is kind of up to how the client uses the classes then.
Right.
Like
yeah.
If you want all classes to be in one place, you have to add them all to a same region, that sort of thing.
Right. Yeah. Yeah. Exactly. And that's what we do. Yes. We kind of just mimicked a lot of what the OpenJ9 shared cache did within the SOM cache. It's sort of like a really tiny sort of microcosmic version of the OpenJ9 class, if you like. I don't know a better word for that, but that's the idea.
Okay, I'll ask one more question, then I guess if others have questions, they can jump in. I wanted to ask about. I know you have a pull request that you've opened. Do you have a plan in mind for how that is. All of the code that you've talked about today in that pull request, is that the sum total of everything, or is it?
Yeah, just about, yeah. Well, actually, I did neglect to mention the fact that I did port some of the port library that was missing in OMR over to OMR. Specifically, the OMR port library prior to this pull request lacked primitives for dealing with like sysv style shared memory scanning arguments. I think, yeah, argscan was one of those. A few things, yeah. I think Dan Heindinga left he posted a request on that PR saying that I should break it down into smaller PRs because right now it's quite large.
Yeah, I was going to make that observation as well. That it's pretty unapproachable in the size that it's at right now. It would be more helpful if you break it down, even if you could just break down the pieces that could be contributed to one component without, like maybe the port library changes, if they're in there, could be separated out, or that kind of flavor of change at least.
Right.
Sort of geographic breakdown.
Yeah, that makes sense. I should have done that originally. Yeah. Yeah, I'll probably start with separating out the port library stuff.
See if anyone else has questions.
I have a question. What is the relationship between the shared cache code that is in the pull request and the work relating to AOT for the SOM implementation? If there is any.
Right. The SOM implementation persists code to the cache and reloads it at a subsequent startup of a SOM VM. So whereas AOT code would classically go to something like an elf file, in this case it goes to the cache and is read back from the cache once the VM is started. So as far as AOT code is concerned, it just serves as a storage medium.
But what is in the pull request is that part of that SOM code base, is it factored out and but also used in that AOT code base, or is it completely orthogonal and like you cannot really there's no there isn't really any reuse of the shared cache code in the PR in the AOT code?
The first of those things that you said. So the SOM++ cache consumes the code that is in the PR. It really just sort of extends and brings together various just features of the refactored cache.
Does that mean if the PR were to be merged into OMR, that could form the basis for SOM++ to then have use a shared class cache built on top of that, that component?
Yep. Exactly.
To that is there to us that's very interesting because well, unfortunately Jan is not on the architecture meeting today. He can speak about this in much more detail. But basically, our interest in this is that we use the SOM as an example of validating the RISC-V port. So there's two ways to validate that the port works at this point. One is through drill tests, and the other one is we run SOM++, like your implementation, on the RISC-V port and see that, okay, well, not only does it work on Intel, but also on RISC-V. So if parts of that universe are ending up in the OMR code base, that makes our proof of validity depend on less external code.
Yeah, okay. So is that good or bad if it depends on less external code? I'm kind of something you want to avoid or pursue.
Okay, maybe a question for offline.
Okay.
I had a follow-on question around the testing for the PR. So I have to apologize. I have glanced through the PR, but I haven't looked at it in detail. Are there tests included in the PR for the various functions in this component, or is it?
There are no tests included in the PR, no.
Okay. All right. Do you think it would be hard to write tests to?
I'm in the process of writing tests against the SOM implementation of the class right now. To some degree, they depend on the SOM++ environment itself. I'm not really sure how the RMR, excuse me, OMR maintainers feel about that exactly, considering that it kind of depends on a chunk of external code.
Yeah, that wouldn't usually be something we'd pursue. It would be like most of the testing at OMR is meant to be kind of testing the underlying facilities of the components, try to establish that they're correct themselves, even, and then people can build on those interfaces and rely on them in principle.
Yeah.
Okay. Well, that may be an area you're asked to at least think a little bit more about.
Right.
The PR is reviewed.
Yeah, that makes sense.
All right. Are there any other questions for Mark? Once, twice. All right. Well, thanks, Mark, for coming to give that presentation. We appreciate you taking the time to put that together for us and give us a little more context around the PR. I think anything you can do to whittle down that PR into smaller pieces would be greatly appreciated.
Yep, we'll do.
Could you also make the presentation available?
Yeah, it's sure. Mark, would you be willing to send us the presentation so we can make it available, or if you can make it available somewhere and post a link in the Slack channel, maybe something like that, or even in the meeting issue?
Yeah, sure. I can do the meeting issue and just post a link to that on Slack, perhaps.
Great. Thank you.
Okay.
All right, that's the topic we had for the meeting today. So I just wanted to sort of wrap things up and thank everyone for joining us on the in this architecture meeting for January 2020. And I look forward to talking to you at the next meeting. Thanks, everyone.
All right. Thanks.